Remember where we left off? We have covered how to stabilize all aspects of our transition state so far, except what we do at the substrate. So let's summarize real quick. In other words, nucleophile. We want a nucleophile that wants to form a bond. We need a strong nucleophile, right? We've worked out the leaving group. We want a leaving group that wants to leave. It'll be stable after it leaves, right? We've worked out solvents and how they affect that. So that's surrounding that. Now we're going to talk about the substrate, the CR3, where R could be H, it could be other R's. We'll define that. So first we're going to look at that. What can these R's be? Let's suppose, so what we're going to do is turn this molecule around. I'm going to show you where I'm looking at it from. The nucleophile is not attacked yet, so it's a substrate still. And we're just going to look at it from here. So I'll try to draw it the same way it is in the transition state. R, C, and then we'll have R, R, and then here's our leaving group. So from the nucleophile's point of view, remember it's going to go at that trajectory opposite leaving group. So it would be looking right here. So the leaving group would be in the back, right? So it'd be like this ball right here. And it's going to say, what do I see as that nucleophile wants to attack that delta plus on the carbon. It wants to get there. What's in its way? Depends on what R is. So these models here, they were computer generated, were built in what's called the space filling representation, because that more accurately describes the space that has to be, something would have to fit through. So for this application, it's perfect because we're trying to see how crowded it is for that nucleophile. So knowing that we're looking from that point of view, right, I'm just going to fill in what these things are. This is the carbon of the substrate, and the leaving group is way back here, right? So that was the leaving group. That sphere that you kind of see right there, that's the leaving group. So I can label that in all of these just so we are clear where it is. Leaving group, leaving group. So we can't even see it anymore because obviously it got filled up, but it's in the back. So this is the other side. We're looking at the carbon. Okay, and here are the H's. Now this is only if R equals H, H, H. All three R's are H, right? R equals H, H, H. This is what the incoming nucleophile will see. So I'm going to write out that it's a space filling representation. You could do this on Spartan, by the way. Okay, space filling representation. So in other words, if R is HHH, it's just CH3. It's a methyl. Okay. Let's compare that to, not all the R's are H. Let one of the R's be another R group, or another carbon. So like a methyl, right? So here, let's draw that out. Here's our CH3. See that? CHHH. Wow, we kept two of them as H's. Now let's replace the other H. Let's say we had two methyls. R equals methyl, methyl, H. So methyl, methyl, H. Or let's say we have no H's on that carbon. It's all R groups. So in this case, methyl, methyl, methyl. There's a word to describe this. So if there's only one R group on a carbon, well, if there's none, it's a methyl, clearly, because it's all H's. If there's only one R group on a carbon, like in this case, it's called a primary carbon, okay? This is primary. So our substrate has a primary carbon with the leaving group. The leaving group is on a primary carbon, a bit represented with one degree symbol. Secondary means we have two R groups, okay? Tertiary means we have three R groups. Now, what I want to also point out is look where we are here. Which carbon is most crowded out? Clearly the one with three big R groups. Okay, So it's harder if I even highlight maybe what that space looks like. Let's do that in yellow. Here's the space available for the nucleophile to attack. And it gradually starts to shrink a little bit as we increase the substrate size. So notice how it's much smaller. So the tertiary was the hardest. And the methyl was clearly the easiest, right? So we're going to be describing substrates in terms of methyl's obviously a methyl, but what do we don't always know what the R groups will be when we have a primary, secondary, tertiary carbon. So we're going to be using those terms a lot. So primary simply means carbon with one other C attached. Secondary means a carbon with two other C's attached directly to that carbon. And you got it with tertiary, a carbon with three other C's attached. Okay, so in terms of who's going to be attacked the easiest for an SN2, methyl gives a lot of space for an incoming nucleophile, as does primary, which gives more space than secondary. Okay. However, tertiary is significantly harder, so I'll put two of those and so we actually don't really see tertiary carbons react in SN2 very much. So in other words, the carbon with the leaving group must be sp3 for a reaction to occur. So we'll always be able to describe them as methyl, primary, secondary, or tertiary. Okay? And not tertiary. So we want methyl, primary, or secondary, not tertiary. Okay? Okay, so now when we're trying to decide, is a SN2 reaction going to happen? You kind of have a checklist to go through of all those conditions that help you decide if that would work. Well, you must have a good nucleophile, right? Moderate is considered pretty good or better, or strong. Same with the leaving group. The carbon cannot be tertiary, and all solvents will show up. But if we get to pick it to go faster, polar aprotic is better. Okay, time to do. So what I'm going to mention here is primary and secondary are good. All right, so what we're going to do, some practice problems. We'll do some of these together. I might save some for later. So let's do this. We're going to notice right away, first of all, there's only one thing right in here, but stuff over the arrow. So remember what I warned you? You need to find your solvent. So that'll get it out of the way right away. And then you need to decide who's the electrophile, who's the nucleophile, right? So when we're doing the SN2 reactions, you're going to look for ID at least. I'll actually write ID. That's ID, solvent, electrophile, and the nucleophile. Okay, we'll label those before we move on. Don't just try to jump the gun and draw something. All right, so solvent is typically drawn over the arrow, but so is also one of the other reactants. So you have to know which one is the reactant and which one's a solvent. And then right here is usually the space reserved for like the biggest organic piece, but it doesn't have to be. We could have put one of the reactants here, like the nucleophile here, and put the substrate over the arrow. So usually there's at least one structure drawn here, maybe two, like A plus B, or it could be A with B and solvent goes to the product. Okay, so you gotta be comfortable seeing that kind of mixed and matched. So it could be A with B, and then we might write solvent often on the bottom, goes to product. This is a really common way to write out the reactions. So I kind of gave that away if you didn't see that DMF is on our solvent list, dimethylformamide. So it's just going to be our solvent. It is a polar aprotic solvent, which is good for SN2, but that is not our high priority. Like I said, other solvents work. We can't do an SN2 on a tertiary carbon. That is a rule that I use to help us. I make sure our carbon's not tertiary. So, but you got to find the substrate first. So I don't want to jump the gun yet. Let's find our substrate. So I found our solvent, our electrophile, which is our substrate. Okay, so our electrophile, it has the leaving group attached. Do you see a good leaving group? If you don't, you can always go back and look for the nucleophile. Nucleophile is usually minus, right? It's usually a minus charge. Maybe a delta minus if you're unlucky. But do you see something with a full minus here? Yes, right here. So this is our nucleophile. It's actually on our good nucleophile list. Okay, so that means this must be our substrate. Where's our leaving group? Find the leaving group. Iodide. That means this is our electrophile. The carbon attached to it is the one that gets attacked. What's the nature of that carbon electrophile? Draw on your H's if you need to. Okay, it has only one carbon attached to it. So it is a primary substrate. We're good to go. We have a primary substrate. We have a strong nucleophile. We even have a good solvent, which we don't always get. So this is definitely going to do an SN2. So it satisfies all those requirements. So now we draw the mechanism. Nucleophile attacks. If you have a hard time drawing it from the back, don't worry. It doesn't matter. It matters for the transition state the most. Just show it attack the carbon that has a delta plus, the carbon with the leaving group, in other words, and show the leaving group leaving. We had two H's on that carbon, so there was no stereocenter. So this is a simple case. Don't even have to think about that. We just draw S, and everything that was attached to it comes along as the nucleophile. That's our new product. Our byproduct means product that formed that we don't care about as much was the I minus, right, from the leaving group. So I'll just put that in parentheses. Byproduct. Okay. Here is a fun case that you want to watch out for. These are really popular and useful. There's only one thing. Solvent's not given. It's not always given, so we have to kind of be okay with that sometimes. So I'm going to say, okay, that can't be the solvent, otherwise a reaction wouldn't happen. So now I need to look for a nucleophile. A nucleophile is a full minus charge. Well, this is an R group right here, and O minus. It's an RO minus, an alkoxide. That's a good nucleophile. Where is a leaving group? Do we see a leaving group? Yep, bromine. Hey, we have the nucleophile and the leaving group in the same molecule. That means the substrate must also have the nucleophile. So remember the leaving group, you find the leaving group, you say, okay, the carbon attached to the leaving group is the one that gets attacked by the nucleophile. That's where we put our delta plus, right? To show that it's about to be attacked by that minus. We can look at it and draw on our H's now. And say, okay, it's only got one other carbon attached, it's primary. It can do an SN2. In fact, it does an intramolecular SN2. Intramolecular. Okay. Intra means within the same molecule. Intramolecular. Molecule reacts with itself. It has a leaving group substrate, sort of electrophilic tail, and a nucleophilic head. So it comes back and basically bites itself and forms a ring. And these are actually kind of fun reactions. So here we go. Swing that around, lone pair attack, carbon with the partial plus. Kick off the leaving group. Be very careful now. We have to draw a ring. Well, what ring? An octagon, a decagon, a hexagon, a butane sort of ring? How do we know? We got a number. Everything that was in the reaction. We started with oxygen. I'm not doing a naming job right now, so I don't care how I number. We can number with, we just have to track it. We can number, we can write alphabetical letters, but I'm just going to number starting at atom 1 right here, oxygen, because it was part of the reaction. It made a bond. It closed the ring, so it's included. And I'm going to number until I get to the atom that it attacked, 6. Therefore, I get a 6-membered ring. We know how to draw those. Hexagon shape. Make sure that one of the atoms is an oxygen, not a carbon, because oxygen closed that ring. Number it again if you like. 1, 2, 3, 4, 5, 6. And we're done. Intramolecular reactions, ring clothing, very, very common. So, and kind of fun, a little different, right? Okay, let's do a few more. Feel free to pause and try to draw the product first. And then come back. I'm going to keep going though, so we have it all in one spot. Okay, so now we have three things again. Let's find the solvent first, get it out of the way. Who can be the solvent? NaCN, that sounds familiar. There is a nitrile contained solvent, but it's not NaCN. That's MECN. Don't confuse that. Na plus, this is a metal bonded to a carbon, non-metal. That means we have an ionic bond. That's Na plus Cn minus. That's not our solvent. DMSO, dimethyl sulfoxide, yes, that's our solvent. It's polar aprotic. So we don't have to look at that too much further. So Na plus, Cn minus. We need to find the nucleophile. Out of everything here, we only have one negatively charged species. It must be this piece. Remember that ionizes. The Na goes away. It's like a spectator. Na plus goes off on its own when it's in the polar solvent. So this is our nucleophile. We can even draw out the Lewis structure. In fact, I urge you to. Makes it more obvious what's going on. So that's our nuke. Now what? We need to find, clearly what's left is our substrate right here. That's our electrophile. Who's our leaving group? Certainly not the methyl. Yes, water, great leaving group. So because it's on a wedge, I'm going to draw the missing dash. I'm not going to do that down here because that's not where reaction's happening. Reaction's happening here, so I care about that stereochemistry. I'm going to label that as my leaving group. That means attached to that leaving group, there's a carbon that has a delta plus. Now, I drew in my H for another reason, because it also helps me visualize if it's primary, secondary, tertiary. So notice that this carbon has two other carbons attached to it. So it is a secondary carbon. Okay. Secondary is good to go for SN2. Water, we know, is a decent leaving group. Cyanide is a good nucleophile. We're set up, this is going to do an SN2. So let's do it. Attack, kick. Water leaves. We had a stereocenter. We had two actually. This one, it did not go to that party. It stays the same. Nothing happened to it. The methyl stays on a wedge. Only the carbon that reacted should be the one inverted. It's only fair. The leaving group was on a wedge. Therefore, the new group is the opposite of the leaving group. So the new group must be a dash. Who is the new group? Cn. Our leaving group left and we made some water. But this is our main product that we would be looking for in the answer key, okay? Okay, one more reaction. I'm going to say this one does not do an SN2. You figure out why. It actually does react under a different set of conditions. We'll revisit that later. But it does not do an SN2. Okay, so we will actually see a reaction happen. I'm going to give you the product now, but I want you to figure out why it does not follow an SN2 mechanism. So the real product is here, but it's not from an SN2 reaction. So we still had a leaving group leave, get substituted with a new functional group, but it can't do an SN2 because it's tertiary and some other things going on here that you'll have to kind of work out. So that means it must have done a different path. Okay, that's kind of the trailer for our next section. It proceeded via something called a SN1, and we will talk about that next. But for now, practice SN2s like crazy, and so I'll put to be discussed We're going to cover SN1 in the next section. Okay, so your job now is to make sure you can identify all the pieces of SN2. Look at the substrate. Is it primary, secondary, tertiary? If it's not tertiary, it can react. Does it have a leaving group? Good enough leaving group, then substrate set. Look at the nucleophile. Is it a reasonably strong nucleophile, moderate or better? Yes, then it can react. Solvent, ideally Polaroid product, but not mandatory. Okay, so as long as those first two things were set, the substrate and the nucleophile satisfied all those conditions, SN2 can happen. All right, so go practice those, and we will meet again to talk about its relative, the SN1 reaction. See you soon.